Right, in 8.6, we get some various other theorems that kind of related to things we've done lately. If you look at oral exercise number 1, they tell you that you've got a root of 2 minus 3i. And they ask you, what other root must you have? Well, if you look at page 377, there is the conjugate root theorem. And the conjugate root theorem says if we have basically 2 minus 3i as a root, we will also have its conjugate as a root, so 2 plus 3i. So if you have a term that has an I in it, it has another one that goes with it. You can automatically know that this one is another root of it, even if you just are told that you have one. If you look at number 3, it's similar. Number 3, they tell you minus I and 2i. Okay, now if you get confused about this one, if you put it in that form, the conjugate root theorem talks about things being in the form a plus bi. So how could we write, for instance, negative I that way? We would write it as 0 minus 1i. We would just write it that way. So what would its conjugate be? Because the conjugate root theorem, again, says the conjugate will be a root. It would be 0 plus I, but how we would really write it would be I. So I'm going to list my answers over here in brackets, okay? We already know these two are roots. Similarly, you have 2i. Well, if you wrote it in this a plus bi form, since there's no number with it, you would say, well, that's 0 plus 2i. So what would be the conjugate? It would be 0 minus 2i, which we would just write as minus 2i. So let me list that over here. So because we've been told that we have these two, we automatically know we have these other two roots there, and that's what we're seeing in that the conjugate root theorem on page 377. All right, on number 7, we're told that this is a true statement, and they want to know how we know it's true. Every third-degree polynomial equation with real coefficients has at least one root. Okay, that means it's an equation that has an x cubed in it as the largest term. It could have another coefficient in front of it, but it has to have an x cubed in it. And it might have other terms with exponents lower than that, or it might not. We just know it has an x cubed in it. How do we know that it must have at least one root? Well, one of the things is if you go look on your calculator and try to graph some cubic equations, they all kind of have an S, kind of a sideways S, and that's not great shape. And so what's going to happen, it's always going to cross the x-axis one time. That's not really that's not really the explanation we need to give, though, even though that's true. If you look at Descartes' rule of signs on page 378 at the bottom, if you look at where it says, it says, let P of x be a simplified polynomial with real coefficients and terms arranged to decreasing degree of x. Okay, so it just means we've got something that's in our case, it's got an x cubed in it, okay? And let me write that down, the x cubed thing. And it may have other terms with it, and it may have a number out here. It might have like 14x cubed or something. Anything could be out in front of it. So if you look at number 1, what Descartes' rule of signs says is the number of positive real roots, that means solutions, okay? So we're talking about roots or solutions, equals the number of variation of sign of px, or is fewer than this number by an even integer. That wasn't quite what I thought it was going to be. There is another theorem, and that's what I thought they were getting at here, that talks about if you look at your highest exponent, and I don't see that theorem in this book, which is really kind of weird. It's the theorem that I'm thinking of says that if you take that exponent, you either have 3 solutions, or you would subtract 2 to get down to the nearest amount that you could have. So 3 minus 2 would give you 1 solution, but if you did 1 minus 2, you'd get negative 1. Well, you can't have a negative 1 solution, so you'd either get 3 or 1. Now, that's a theorem your book doesn't discuss, which is exactly what I thought it was going to do, and it didn't. But what you could do, you could use Descartes' rule of signs. So there is this theorem here in the book, and I guess this is what they're intending for us to use. Descartes' rule of signs says how you're going to count how many times the sign changes, okay? And you always start off with saying that's one sign because it's a plus. And, even if it were just as simple as x cubed, maybe it didn't have any other terms, you'd at least have one a sign on that term. And what it's really saying, So we could know that there's a sign on that term, so there's at least one solution. Here's what they're really getting at. What if I had 14x cubed minus 2x squared plus 3x minus 1? Well, there's a sign change there, a sign change there, and a sign change there. So there's 3 sign changes. That means that we would either have 3 solutions because there's 3 sign changes, or you could decrease it by an even amount. So 3 minus 2 is 1, okay? And if I did 1 minus 2, it'd be at negative 1. So this is either going to have 3 solutions or 1 solution. Now, it's kind of confusing because when you look down at the example I gave of x cubed, you think, well, there's not a sign change there. If it's just got one term, you know it at least has one solution. I think it's kind of hard to think about Descartes' rule of signs there, so that's probably not a good example what I picked here. But let's see. I'm trying to think of other examples. The book gives you some examples of it. What's interesting about the book is they really don't go into a lot of explanation on this, so it makes it kind of hard to tell you, look at this theorem and see if you can understand it. But we would at least have one solution for anything possible. But you could say that you could have for this cube one, if we look at this example right here in brown, it's either 3 because of the sign changes, or it could be an even number less. So 3 minus 2, 2 is the smallest even number, would give you 1. That's really what's going on there, though they really don't give you enough examples in the book for you to see that. Okay, so let's look at some more with this Descartes rule of sign. If you look at number 11 in the oral exercises, they give you this. Well, everything's going to have at least one solution, okay? That what Descartes' rule of sign says is look for a sign change. Well, this is positive to positive. This is positive to positive. There was only one sign change there, so that means there's only one solution. I mean, there wasn't even a sign change. I shouldn't even say there was a sign change. It's all positive, isn't it? Well, you're at least going to have one solution, and in this case, you know you're not going to have more than one solution because there wasn't a sign change. Okay? Let's look at, we can look at number 13 and do it too. This is always a little confusing, especially when the book doesn't give you very many examples. All right. If we look at this one, everything's going to have at least one solution, but let's look here. This goes from positive to negative, so there's one sign change here, and then it goes from negative to positive, so there's 2 sign changes total. There's another one there, so that's a total of 2. So this one's either going to have 2 solutions, or remember, you have to subtract an even number. So 2 minus 2 means there would be 0 solutions. This might not have a solution at all, not a real number solution anyway, and they're talking about real number solutions. So this could have 2 solutions, or it could have no solutions. And again, it's because we said that it went from positive to negative there, so that's 1, and negative to positive there, so that was 2 changes. So 2 or 0 is the answer there on number 13.